Alright, the other Jupyter lab notebook that I've created is one for the EEXIST system. Um, and this is built on a pure Python kernel instead of a custom kernel. And it's basically set up as just a series of Python modules that you can use to create and customize an EEXIST module. You can control its physical extent, its granularity in space and time, the effect of karma, and then there's also a genetics laboratory that sits on top of that lets you create populations of individuals and control things like the population size, the mechanics of mating, defining code that determines the fitness of each individual, how the next generation should be created from the previous, mutation rate, all those kinds of things. And this is also available in Binder. It took a while to start, but I took a break and came back to it, and it started right away this time. So your mileage may vary, but like all of these Binder notebooks, they're driven from a publicly available open source GitLab repo, and you'll find descriptions of those repositories in the description on YouTube. So let me go ahead and do the non-simple interface, and this begins with just sort of a introduction to the whole EEXIST system. There's links to the online book that you can download for free, the latest edition of it, and some website based descriptions of the project. But you import exist, and then you can construct an instance. You can set the karma. You can display what the system looks like, and in this case we're displaying the volumes of chemicals in each spatial location. We can set the amount of source and destination chemicals either in an individual tube or in the tubes within some range, in this case from 0 to 30. We're setting source and destination to 5 on each one. We can step the simulation forward by whatever our DT is. And so this first chapter basically just runs through a simple example where we have a baseline set of chemicals in this range from 0 to 30, and then we have a transfer instruction here at 35 which says transfer from location 10 to 20. And we can see a tiny little blip here where some chemicals came from location 10 presumably into location 20, but it's really small and hard to see. But we can increase that, and so let me go ahead and actually run these cells. And so here's where we made a small transfer and a little tiny blip down there. So we can also do animations of how the system behaves over time. So let's step the system forward 20 time steps, but we'll use this do display argument and set it true to actually give us an animation of how the system updates. So we can see that the kernel is busy right now. These animations take time to run, but once they finish, we can hit the play button and kind of see how the transfer happens. And if we just take this to the end, we can see that more chemicals came out of location 10 and moved to location 20. And so we can start doing experiments. Here's a case where we, instead of just having a single destination from 10 to 20, we have a range of tubes specifying destinations. And so if we step that, we get a more dramatic transfer. And if we do a series of those, we'll just do 5 steps here, and we can see what that looks like. And it pulls off all the chemicals from a 5, transfers them to 20. And then we have some experiments introducing the notion of karma. So karma is a blurring of the locality of where effects occur relative to some cause. So instead of a cause having a single isolated effect, the effect is spread out across a number of cells. And so if we run this cell, and we've set karma to be 1. Instead of just transferring from 10 to 20, it will actually transfer chemicals from a region around 10 to a region around 20. And so we get a distributed effect. And the effect is most profound at the location where the cause was directing the effect, but there's also effects nearby. So that's the karma aspect of the system. And so we can play around with these in here, and you can run these simulations and look at the effect of different instructions. So then the next chapter introduces the genetics laboratory, and this is a really rudimentary set of documentation. This is just the README from the GitLab repo. But basically these are functions we can call to set up the parameters for an EEXIST instance, to convert between a spatial coordinate and a bin number, or back the other direction, to advance the simulation, to adjust karma, some tools for pre-filling tubes with interesting values, clearing tubes, setting a tube or a value in a range of tubes, reading tubes, and so on. And this also introduces the notion of a bias, so an offset on the instruction specified by the amount of source and destination chemicals. Again, if you want to understand all this stuff, take a look at the book, download it, it's a free PDF. It goes into much more detail about all of this. But we can look at all of those and adjust all of those parameters of EEXIST. And then there's the notion of an individual, which is just an entity that has an EEXIST instance inside, but also has a genome, which is a collection of biases across the spatial domain. And then there's the notion of a population, which is just a collection of individuals, each with their own genome. And populations come with tools for mating individuals, assessing fitness, killing off the least fit, allowing the most fit to breed, and so on and so forth. And so this is just kind of documentation. In chapter 3, we actually play around with some evolutionary experiments. We make a population, and we have a chunk of code that we've written here to basically let us specify 2 inputs to this system. So we're going to evolve an XOR gate, so we need 2 inputs, A and B, and the system we're using is for A, if we want to store a true value, we set the amount of source to 5 and the amount of destination to the amount of source to 30 and destination to 10. Otherwise, we set the source to 10 and the destination to 30, so we modulate the ratio of source and destination chemicals in these tubes between 5 and 10 for A, and these tubes between 15 and 20 for B. And then our test code basically loads in those values. We set all the other tubes with just a baseline of 5 source, 5 destination. Load A and B into EEXIST, step it 50 times, and then we measure the chemicals between 25 and 30, and if the average chemical level is 25 or more, we take that as true. 15 or less, we take it as false. And so for each of the 4 possible tests, 4 rows of the 2 input truth table, we run this test, we determine what the system is claiming the output is, and we get a score based on whether that's correct or not. So this gives us a fitness measure for each individual, where each individual has its own set of initially random biases. And then the main program, we basically we have a random seed, and we basically just do a test, right? So we can specify a file name for the test, and the main evolutionary loop, main test. In this case, we're starting with a population of 10 individuals, karma, spatial domain, 15 genes, temporal granularity. We start off by randomizing the bias values for each individual. And then we're going to save the results of this in a file And so our do more loop is basically run the test code, right? This system up here. Run the test code on the individual, write some information into the file, make a new generation, and continue. And so this loop will just run until we interrupt it, and we'll continually test each of the individuals. So as it runs, we're writing a file XOR2, right? So start test is this code up here. Takes a file name and then just runs the main test in a thread so that we can see what's happening here in the notebook, but we can also execute new cells to stop it. So we started running this, and here's the scores on the individuals for generation 1, right? These are all random genomes. The best score is 60%, and we continue like this. So, you know, XOR evolution, if you just have a circuit that outputs false, it's right 50% of the time. So 60% is not terribly impressive. After a while it bumps up to 61, and then 69, 73, 76, 83, and so on. So I let this run for a while, and after 50 iterations, did the stop test to terminate it. And then here's a synopsis of the best scores from each generation. Generation 39, we hit 84%, and we can analyze these individuals. So back at generation 19, individual 4, here's some code that basically just looks at that individual. So here's what the biases look like. You can see the effective mutation, so pretty high mutation rate. And then in our 4 test cases, false, 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 true, true, false, true, true. Well, we got 4 for an output here, which should be false. 32 should be true. That's good. 19 should be true. 15, well, that should be false. That should be lower. But if we drew an artificial line, like, you know, between 16 and 19, the values below that line are false. The values above are true. We've got an XOR, right? Generation 20 doing a bit of a better job. So 7 and 8 for false, 22 and 29 for true. So that's pretty clearly in the range that we're looking for, except we wanted true to be 25 or higher. So we can go out to generation 26, and here, you know, we've hit our target range. The true values are bigger than 28, the false are smaller than 8. So the more this runs, the better job it's doing at developing this exclusive OR gate. Here's generation 39, this is our best score, and the false values, you know, 2 and 9, true is 31 and 30. And you can run these simulations and sort of see how the system gets to each of those conclusions. We can actually do that. I don't want to rerun all of these tests up here, but I'll go ahead and start the system. So we'll do that and that, load our support code, load our main evolution loop. I will not run this because we've already got XOR2 sitting in here as a result of this, so we can just jump to the analysis part. So here's how false and false plays out. So it's generating our animation right now. And if you do this on your own, if you just download it and run it in Python directly, it's a fair bit quicker usually than what's running on Binder. But Binder is very convenient if you just want to run this from the web and play around with it. So here, you know, we've started off with false and false. False meaning that we've got a low level of source and a high level of destination. And we're looking at the amount of chemicals in this output tube. And you can see what happens as it runs. The amount of chemicals stays pretty low. That ends up registering as a false. If we load a false and a true, we would like to see that as this runs, the amount of chemicals gets above some threshold so that it registers as true. So this is running right now. And I'll go ahead and let these other ones run also, so they're there when we're ready. So here we've got false and true, and if we run this, we see a lot of chemicals coming up in this target region. So false and true is registering as true, so that's a good exclusive OR. And then true and false should do the same thing. Now it's not doing exactly the same behavior, right? But it's still registering as true because the amount of chemicals at the end of 50 steps is above, our threshold line. But the shape of this region's chemicals is quite different between true false and false true. But they both end up registering as true. And then when we put in true true, we want the output to be small again. And so it initially starts to fill up, but then the volume of chemicals shifts seemingly over to the left, and the amount in this output region ends up being relatively small. So if we just go to the end here, the average across this region is below our threshold. So that's a simple exclusive OR. Chapter 4, we evolve a 3-input NAND gate, and this is a pretty simple evolution, even though it's a fairly challenging target, because remember, a NAND, we want it to always be true except when all the inputs are true, and then we want it to be false. So there's two challenges there. The second challenge is that when we have a lot of chemicals in the inputs, we want very few in the output. The bigger challenge is if we had a circuit that just always flooded the output region regardless of the inputs, it would be right 87% of the time. And so evolving something when your fitness metric gives a minimum score of 87 for a circuit that does nothing, that's a little bit challenging, but nonetheless it evolves pretty quickly. So we've got 3 inputs and pretty much the same setup. Flood the whole region with 5 source, 5 destination, and then 3 input regions for the 3 inputs A, B, and C. So the input regions are 4 to 8, 12 to 16, 20 to 24, and then the output region is 32 to 36. And again, above 25 is true, below 15 is false. And then on evolving that, first round 69%. Well, we would hope that we'd get at least 87.5%. It actually takes a while to get there, but not too long. So around here we're getting 86, 87%, and then we get up to 88, 90, and then jumps up to 93, and then we get 100%. So actually pretty close to 100, it's 99.6%. After 81 generations, we've got a near perfect score. And if we analyze that across the 8 cases, right, true, 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 and in the false case, the chemical level drops from mid to upper 30s down to 2. So that's a nice solid behavior, and you can run that and look at some of these particular examples. Again, it's a notebook, so you can design your own experiments, you can dig into these things as you like, and so on and so forth. And then the last experiment here is a 3-input XOR gate, and this one actually took a while. So all of the parameter choices, they're basically random, right? I have no reason to believe that we should look at 32 to 36 for our output, or set up our input regions in these particular places. They're mostly just first stabs at something, because you got to have something to work with, and ran some tests and they seem to work well enough. Are there other regions that would work better or worse? Probably. That's all stuff that can be researched. So yeah, a random seed, and I'm defining initial seeds in here so that the behavior is reproducible, so that when I run an experiment and I get a certain result, you can run it later and know that you should get the same result. So that there's typos in here. The initial seed was 371, not 37. But same idea, exclusive OR, and the fitness measure is correct answer is just, A XOR B XOR C, and we compare it to the value that we read from the bins. And if the answer should be true and the value is bigger than 25, we bump up our score. If the answer is false and the value is less than 15, we bump the score. Otherwise, we leave it the same. So this ran for a good long time, and I didn't have to go this many steps. Actually, around 113, we got a pretty good individual, but I think I left this running overnight. So generation 112, we evolved some individual with 89%, and that's as good as it got. But it continued doing multiple generations out to almost 400. But then if we test individual 0 from generation 113, exclusive OR again, so false, true, true, false, true, false, false, true, pretty good. This value is a little lower than we would like, but it's still above 15, and the false values are well below 15. So that's 3 input XOR. So if you're interested in this, go ahead and pull up some of the documentation and take a look at that, and you can dig into all the stuff that's happening, and there are a bunch of other experiments you can run. But anyway, that's a playground for exploring some of these concepts.